Hello, everyone. So, welcome to the lecture of file system implementation. Let's say one day you got up and the first thought you had in your mind because of a very sweet little dream you had was, let me design a new file system. What a great thought, right? What a great dream. Many of you might be thinking now, why will I get such a dream? And why would I call that as a great dream? Maybe if I got a dream that I was a millionaire, that might be the great dream. Well, let's say even if you got that, then in order to be a millionaire, you got to have some unique idea that might be able to make you reach to be that. And that unique idea was designing a file system. So now that we stick to this idea of designing the file system, with a great dream or not, let's see how we would go about doing that. If you want to implement a file system, there are many design decisions that you would have to take because file system is a very key entity that decides how the data is stored, where to store the data, and upon a request, from where to fetch that data and give it to the user. This doesn't come at an easy cost, right? So basically all the internal organization decisions of where to keep the data, how to find the data when required, how to update the data to keep the most recent valid copy, and so on and so forth, needs to be taken by file system. So let's get into this interesting job of designing our file system. How we would be learning about these concepts is we would discuss different critical policies which would help us to implement or which are very necessary to implement a file system. We would see from the problem perspective, like what is the problem and what are our different options to solve that. We would discuss few straightforward option with a case study based discussion where we would take examples or learnings from very popular initial basic file systems, such as VSFS. The acronym itself is elaborated as very simple file system, VSFS. So we would learn from those systems, we would take some scenarios, and definitely, as I mentioned, that learning about how to implement a great file system is all about making correct design decisions. So for every problem, there are multiple ways to solve that problem. We would be discussing some of them. We may be discussing some of the alternatives for each problem, but the goal throughout this lecture is to keep your mind running at its fastest speed and keep thinking of, is there a better way to solve a problem? Who knows? You could invent a new idea. You could get a new idea over which you could invent the best performing file system for our future storage, right? So let's jump into our task. Now, sticking on to this idea of I want to implement a new file system. What are the things that you would need? We know that a file system is responsible to provide an interface for basic operations, like the user should be able to open a file, read a file, write a file, delete a file. So definitely we need to provide these access methods. Second, now file system is responsible to store and retrieve files and directories, right? So what do these files and directory consist of? It consists of and data that matters to the user. So second most important thing is while designing a file system implementation, is, well, what data structures do you use to design this underlying layout of content on the storage devices? So access methods, that is, how does the file system maps the calls made by a process. These calls are calls such as open, read, write, close, and could be few more. So how do we map these calls made by the process? Map to what? Where are we mapping, or what are we mapping these calls to? Map these calls to the data, right? And when we say mapping these calls to the data, that data resides inside some particular data structure. So if you are able to map these calls to that data structure, we would be able to access that data. So which structures are we using to read, write during the execution of any particular system call? That would be a very big entity in deciding how good is this file system performing, or how reliable is this file system. I read or written during the execution of any particular system call. Would decide the efficiency in terms of performance, or it would decide the reliability of data on that system. So now that we have seen that, okay, we want to implement these access methods. Implementing these access methods means mapping these system calls to the underlying data structures. And how we map this, or how we implement these access methods, would predominantly determine our performance of the storage system as well as the reliability of the storage system. So we see that, okay, we want to map these calls to the data structures. So what data structures do we want to use? That is also a very important, another critical decision, right? So that brings us to the second important thing that we need to worry about if we want to implement a good file system, is the design decision of what types of on-disk structures are utilized by file system to organize its data. And the byproduct of data is obviously the metadata, right? Like, as we know that every file has a unique inode number and inode structure, that is itself a metadata. So we want to organize data and metadata as well. Now, what are different possible data structures? Any thoughts? Any ideas? Well, a simplest possible data structure could just be an array, right? So we could have simply arrays of blocks or other objects. Why blocks is because we know that the storage device could be visualized as just a collection of multiple blocks, where a block is the fixed size space accessible on the storage device. So we could just have a file system, and the data structure that this file system maintains is just arrays of these blocks. Well, one of the primitive file system was designed exactly on this data structure of arrays, called as VSFS, which stands for Very Simple File System. Very simple, right? Just on arrays. Few other more recent and advanced file systems, such as XFS, uses data structures, underlying data structures that are tree-based. So different tree-based structures, such as V-trees, could be used to organize this data and metadata residing on the disk. Now, you could think of many other data structures which you could make sense and reason about, that they also could be good candidates to store this data and metadata that resides on the disk. So they would be good candidate to design file system with. That's a good thought, keep thinking. So now once we know that we want to have these data structures, and then we want to map the access methods onto these data structures, let's take a very simple array-based organization of data structure. Like, let's take array data structure and let's see what are the different organization tasks that we could do with that in a simplistic fashion. So as an overall organization, we can visualize the storage disk as just multiple blocks, right? All of same size. And if this entire disk is divided into blocks of same size, let's assume that size of each of our block is 4 KB. And if we have 256 kilobyte disk, then definitely we have 64 blocks. So from 0 to 63, we can just number them in an incremental order. So now with the 64 blocks, each of 4 kilobytes, what do we do? how do we arrange our data and metadata onto these blocks? So definitely we know that the core purpose of any storage device is to store the data that matters to the user, right? Whatever data that user wants to save for longer period of time, we have the concept of storage device to comfort that. So definitely we want to store the data that matters to the user in most of the blocks among these 64 blocks that we have in our storage device of 256 kilobytes. But can we use all the blocks to store the data? Well, if we do that, then there is a big problem. Then how would we store the information about where what data is stored so that we would be able to go and retrieve that data whenever required? Do you think it makes sense if we use all the 64 blocks to store the data that matters to us? So making them as data blocks, let's call it data blocks. In that case, whenever we want to fetch a particular data from this disk, we would have to search all these blocks and see if the data that we are looking for is there in that block or not. If not, then go to the next one. If not, then go to the next one. Does that make sense? No, right? That would be the worst performing method to store the data. So we don't want our file system to be one of the worst ones to start with. So definitely we need some metadata about this data that matters to the user. And what is this metadata doing is it would help us somehow to give pointers to where the data that we are looking for is stored. So we need to have few of these blocks reserved for the metadata, but still we want most of them towards storing the user data. So let's say we are storing user data in 56 blocks that we reserve for that. And we are storing metadata, that is data about this user data. And we reserve 8 blocks to store these metadata. So that sums to 64, right? Now, what does this metadata stores? This metadata stores things like which data blocks comprises a file. Let's say if the user says that I want to read file foo.txt. So we should know that what are the blocks in which this foo.txt is stored, right? Things like its owner and access permissions. Not all the users on that system will be authorized to access all the data. So every file has its owner and their files access permissions are accordingly distributed. Few files are read-only, few files are read-write with read-write permissions. So we could store like such information into this metadata. And we could store things like last modified time, etc. So basically later we can visit this things that we want to put inside the metadata. But basically, if we can think of any information that we can gather about the data that could help us to make this file system more efficient and more reliable, then well, it's worth to have that information into the metadata, given that that information is not too big that this metadata would consume most of the part of the disk living very less space or comparatively much lesser space for the user data, then it would not make sense. So we want to add something that's really important to us, but also we want to be mindful of how big this information is to this metadata that we are storing here. Now, one of the obvious thing that we would definitely need, like all this information inside the metadata, could be stored inside our inode struct. So one very important thing that is part of this metadata is inode itself. Let's say out of the 8 metadata blocks that we reserve, 8 blocks that we reserved for metadata, we have 5 blocks reserved for inodes. Now, note that these inode is just the struct, and typically they are not very big. So depending on how many inodes that we would be able to store in this 5 blocks, that would somehow dictate maximum number of files we could store in this disk, right? And let's say if each of our file is very small, then we might be wasting the 56 blocks that we reserved for the data. But contrary, if we can balance the number of files to do a proper utilization of the capacity that we reserved for the data blocks, then it's pretty fine. So very important thing to note that this inode struct by itself is not very big. So just 5 blocks are more than enough to store the struct for all the files that exist in the 56 reserved data blocks. Usually the inode struct ranges somewhere between 128 to 256 bytes, very small. Thus, how many inodes could be stored in 5 blocks that we reserved for that? Each block is 4 kilobytes, right? So 4 kilobyte block should be able to hold 16 inodes. A simple mathematical calculation of 4 into 1024 divided by 256, that's equals to 16, right? Therefore, if a single 4 kilobyte block is able to hold 16 inodes, then 5 of those should be able to hold 16 multiplied by 5, which is 80 inodes. What does 80 inodes mean? We know that every file has this unique inode number and its own inode structure, right? That stores details about this file, such as file size, when was this file last modified, things like that. So if we have 80 inodes, that means we can store max files equals to 80. So we can store 80 files. Now that we know that, okay, our disk is just 256 kilobyte. So being able to store 80 files on a 256 kilobyte disk is pretty decent, not bad. And also note that if the capacity of the disk increases, the same data organization structure, if you maintain the ratio of number of blocks that you dedicate to user data, same as what we have here, to the number of blocks that we dedicate for the metadata, then with the same ratio or the same proportion,
we would be able to, for a larger disk, we would be able to accommodate even more number of files. So it's proportional to the capacity, all the calculations that we are doing over here. Because definitely if we have a larger disk, then we wouldn't be using just 64 blocks out of that larger disk, right? We'll also have more number of blocks. More number of blocks means when we put them into this ratio of user data upon metadata, then we would have more number of blocks towards user data as well as more number of blocks towards metadata. And that eventually then means if we have more number of blocks towards metadata, we can dedicate more number of blocks towards inode. And more number of blocks towards inode means more number of files that we could store on that larger disk. Now, what is another important metadata structure that we would want to store? Now, remember, we have 8 blocks reserved for metadata. So definitely out of 8, 3 of them, we didn't just keep to waste them, right? So there should be some intuition of why we just used only 5 of those 8 towards inode. So the remaining 3 are reserved for some better purpose, right? Can you think of a better purpose, or can you think of some another metadata, other type of metadata apart from inode that would be a fruitful decision to store?